We start with linear regression. We call it linear because it's a model that tries to understand data in terms of a line. Basic terms that we are going to discuss today for this topic. Let's visualize and come on the same page for those terms. Assume these are the data points. On x-axis, we have independent variable. Y-axis is the dependent variable. If we fit a regression model, it looks like that. A regression model is characterized through several features in numbers. First one is the weights of parameters. Line number 1, y hat equals 4.3 plus 0.83x. So x, independent variable, is here. When we multiply it by 0.83 plus 4.3, we get an estimate of y. This is a linear combination of different parameters. The first parameter is referred to as the intercept or bias. The other parameters are the weights of individual variables in the model. For now, we are looking at a simple univariate data. The second number that we look at when we discuss regression is sum of squared errors. How do they look like? From every data point, if we draw a projection on the regression model and square it, it will look like this, the red squares. If we sum all the squares up, it becomes sum of squared errors. These red boxes are individual errors for each individual data point with respect to the model. Summing them up will give us a large red box. The characteristic of the regression model is that this is the best fit line that produces smallest possible red box of squared errors, SSE. Another number that we look at when we talk about regression is R square. R square is a ratio of two numbers, SSR and total SS. Let's look at total SS first. If we don't have a model, we will assume that the dependent variable's expected value is the average value of the data, which is this gray line. We draw a perpendicular projection from every data point to this gray line and square it. Sum of these gray squares will give us a large gray box. If we don't have any information about the independent variables, this is the best possible estimate for y that we can make. And this estimate will give us total sum of squared errors. In this particular example, that is 4068. Looking at SSE and total SS together, you can imagine a ratio. If we subtract these red boxes from the gray boxes, we get a number, SSR, sum of squared residuals. This is the amount, the benefit amount that we get from regression model. Regression model gave us this benefit of reducing the error as SSR, which is difference between total SS, the gray boxes, and SSC, the red boxes. The ratio of SSR and total SS is R squared. R squared is a number that can lie between 0 and 1, just like correlation. The higher, the better. In plain language, we can say that R squared represents the health of linear regression model, how much it captures the variance in dependent variable, 85%. This particular model is capturing the variance 85%. To see the effect of R squared, to see the effect of data on R squared, we can play with this data. Would you like to make this model a little bit more healthy? In that case, we put a number very near to the line. Another data point here, another here. You can see R squared is increasing. What if I give some data points here? What happened? Did you notice? This particular data point changed the linear model. R squared came down to 0.36. Only because of this data point, the linear model lost its power. It explains only 36% of variance in y now. But you can immediately see that this data point doesn't belong, right? It looks like an outlier, which is another related but for now tangential point. We will come to that point later. But for the sake of explaining how we see R squared in terms of a regression model, you can now visualize in your head for even a multivariate regression model how R squared will tell you the goodness of the model. Another number you can see here, R squared adjusted, adjusts with respect to the number of parameters. If we put more parameters, it penalizes the original R squared and give us a little bit less number than the simple R square. The reason is that if we keep adding independent variables to the model, even if they are random variables, I mean, they have no relationship with y, still R square will keep improving. To mitigate the effect of unnecessary variables added to the model, we use adjusted R square. There is another number, F ratio, which is really not as far as we want to go today, but later we will come to it and I will explain in a later module. One more thing, before we leave this tutorial, let me draw some points first. There is a positive relationship between x and y. We read the model in plain language like this. If x changes 1 unit, y changes 0.65 times x, because the coefficient or weight of x is 0.6573. If we don't have any information about x, we don't know the value of x, we are going to use only the intercept of the model minus 6.1 would be the estimate when x is 0. Almost always we don't have access to the whole population. Let's see, we have a population of these data points and we want to sample this population. This is the data available to us. The grayed out points are not available. If we sample again and again and again and keep doing it, every sample of the population produces a different regression model. If I draw 100 samples from this population, IID samples, the regression models corresponding to each randomly drawn sample from this population will correspond to a certain confidence interval. Do you think till now it's been 100? Maybe 50. Anyways, let's assume we have sampled 100 times and we have 100 different models of reality. Now you can see all these models are not way different from the original red line that is created when we have access to the whole population. They all follow, if the samples are randomly drawn and x, the independent variable, follows a normal distribution, in that case, they will all fall within certain bounds. We call that confidence interval. This particular very badly drawn blue line is the confidence interval that will contain all possible models sampled from this population. So if we say 95% confidence interval or 99, we can change it here. The randomly sampled data produces a model and all those models will lie within these bounds 95% of the times. This is the interpretation of 95% confidence interval. Due to some error in the script, this line looks like broken, but it's a very smooth originally. Let me try again to, yeah, this time it looks smoother. So this is the confidence interval for sample data points. Out of 100, maybe 5 lines will be out of this blue band or confidence interval. 95 lines will always fall within these bounds. Recap. Linear regression is called linear regression because it's a linear combination of different parameters multiplied by the data feature vector. The interpretation of each weight of corresponding feature, each weight is that given 1 unit increase in the independent variable, the dependent variable will increase as much as the weight. We characterize a regression model in terms of sum of squared errors, which are these red squares, and R square captures the health of a model in terms of its power to explain variance in dependent variable. Dependent. Why? So these few concepts we will use in again and again during our following discussion when we learn to derive mathematically how we come to these two numbers, 0.67 and minus 4.5. How do we get and why they are the best possible numbers that we can have for a given data set, as shown here. Before moving on, would you like to stop me and ask a question? Why do we call regression regression? Where does this regression word come from?
Like regress to the mean.
Perfect. Mean of
the population.
That's right. So you can see this particular line is passing through this red point, which is mean of X and mean of Y. The story behind regression word is that a guy who gave formulated regression named Francis Galton did very interesting experiments in genetics for the then queen to support a strange hypothesis. And one of his experiments were on humans. He proposed that for humans, tall parents tend to produce tall kids, and short parents tend to produce short kids. But extremely tall parents will produce, albeit tall kids, but they will be shorter than their parents. And extremely short parents will produce short kids, but they will be slightly taller than their parents. And he collected data from 17 different counties and neighborhood countries in Europe. And that data is publicly available. You can load it in from sklearn or in R or just Galton's parent-child data set. Google it. You will see it's readily available, published. And textbooks usually use that data set to explain the concept of regression. So introduced by him, later from different angles, people came to the same conclusion using linear algebra or Bayesian statistics or maximum likelihood or analytic standpoint that these particular coefficients can be the best coefficients given certain assumptions about the data. And all these points, if we have all the points till eternity, all the population, we will see that they tend to fall back to this red line. That's why we call it regression, falling back to.
Professor?
Hi.
What does confidence interval mean? Does it mean that if the line moves away from that interval, the R square will drop down 95%?
Confidence interval has nothing to do with R square. It tells us something interesting about population. So let's say these points with the yellow boundaries are our population, right? And we know that we never get access to the whole population data. We always work with sample data, right? So to simulate, in order to understand the effect of the interpretation of confidence interval, we assume, although it's very maybe simplistic assumption, we assume these points are total population. And when we sample, some of these points are grayed out. So 90% we keep, 10% we forget about them. And based on only the yellow points in this sample, the grayed out points are not included in the model. The new model is this gray line. You can also notice the parameters here will change slightly when I sample again. Oh, I'm not updating those. These are the population data parameters, but the sample data is producing these gray lines. I keep sampling and producing, keep sampling and fitting the regression model. And if I do this 100 times, statistically, 95% of those 100 will be within these blue lines, confidence interval lines. The blue lines are the confidence interval lines. Only 5, there is a chance that from the sample data, we get a line that falls out of the blue bands, and there will not be more than 5 lines out of 100 that fall out of this blue band.
Okay,
that is the interpretation of. Till now, I couldn't get one that is going out, but I do want to show you. Let me stick on this a little more, or we can increase confidence interval, but it breaks down. I don't know, my script is really not helping. So for 99%, we can have even thinner. We can have thinner confidence interval and a data that is a little bit more spread out to see the effect of sample with respect to population. So in reality, we will be always working with samples, not the whole population. And that's why when we create a model, your employer or your client will ask you, how confident are you in this model? So you will say, statistically, my model is, I'm 95% confident that no matter tomorrow, next year, following year, whenever you sample this population, these parameters will be slightly different, but not as much. So the new parameters will be within these two bounds. Upper bound, upper blue line, lower bound, lower blue line. A similar concept is of the prediction interval, that is for y. So y's value will always fall with using these models. Y's value will always fall within these green lines. Given certain assumptions about the data that I will talk about again and again during our following discussion, but these are the few key points that I wanted us to have same understanding about. The parameters, sum of squared errors, R-square, and confidence intervals.
Okay, I got it. Thank you, Professor. And what is the K in the R square ADJ equation? The K.
Very nice question. Very nice question. Number of independent variables.
Number of independent variables. Okay. Okay.
For now, it's in the simplistic tutorial. We have just one variable, but in reality, we have hundreds or thousands, maybe, when we may like to regress. And at that time, adjusted R-square will penalize unnecessarily adding independent variables to the model to increase R-square. So in practice, we report in our results adjusted R-square.
Okay, thank you.
It is always slightly lower than R-square. This kind of penalization or kind of regularization or smoothing we will see as a recurring objective in machine learning. In one way or the other, we try to downgrade our estimates.